In this video, we'll be talking about some systems engineering design tools, which are really useful for creating our requirements and our work allocation throughout our system engineering design process. Our first design tool that we'll look at is a staple of project management, and it's a WBS, or work breakdown structure. Essentially, it's a tree-like hierarchical structure which maps physical work packages or parcels of work that need to be done. So it shows a hierarchy of work and how different work packages are decomposed. This can be really good for resource allocation and for costing, because essentially the cost of a project in large part is a sum of all the individual parts or the sub-projects that need to be created to create the full project. Here's a sample work breakdown structure. It shows the construction of a house, and there's a whole lot of areas that need to be constructed for this house to be complete and successful. For example, we have things like the internal, and there we have important things that need to be created, important parcels of work like all the electrical wiring, all the plumbing, and they each have their individual costs based on each room and area that needs to be plumbed and wired up. We then have a work parcel related to the foundation, and in there we've got sub work areas like excavation and preparing the area for the foundation to be laid, and then the foundation being actually installed in there. Then we've got things like our external areas, so our third work parcel there, which is things like masonry and all the trimmings and things of painting and putting up gutters and things like that. Now these are all things that we need to do in a house, a work breakdown structure for a house. But most of our systems engineering projects we can visualize in the same sort of way of physical things that need to be created to actually deliver the system. For a system involving maybe a tank or something like that, we'll have things to do with the chassis, we'll have things to do with the weapon systems, we'll have things to do with the electrical systems, we'll have things to do with the rolling and mechanical systems that actually are involved in the drive system. All of these things could be covered and encapsulated under work breakdown structure, and can allow you to farm off work to other subcontractors of this subcontractor is going to be looking after this section, and this subcontractor is going to be looking after this section, for example. Our next tool that we'll be looking at is the RBS, or requirements breakdown structure. Now, our WBS that we just looked at was looking at physical breakdown of work. Here we're looking at logical or functional requirements and breaking down the system in a tree-like structure of logical and functional requirements that the system needs to be able to do. And we map these down from our overall mission. So once again, we have this hierarchy of requirements. So our system mission there sits at the top, and then we have requirements 1, 2, and however many that we have, and sub-requirements that flow from each of these. So our requirements breakdown structure is great because it clearly shows how the requirements link back to what the overall system mission is, and produces this hierarchy of requirements. And so any of our low-level requirements should be able to be traced back directly to high-level requirements and somehow perform or enable the mission to actually occur. So here's an example requirements breakdown structure. In this case, we're creating a class-leading, environmentally friendly family car with ample space. And so we've got a few requirements there. Firstly is the requirement that the car will be environmentally friendly. And we've got sub-requirements there of relating to the emission standards of the car and fuel consumption of the car. And it's to a measurable standard below what the competitors are actually working with. So it's class-leading in that regard. And then we're talking about ample space that the car needs to have. So talking about the interior and some qualification there of who this car actually needs to suit, and boot space that this car needs to encompass. And we could go on further and further with extra requirements and extra sub-requirements that flow from each of those. Now, we saw in that requirements breakdown structure that it's this hierarchy structure with labels in there. So there's, for example, requirement 1 and requirement 1.1, which flows from requirement 1. And so we can very quickly, using this sort of labeling method, trace back our lower level requirements to parent or upper level requirements. So very handy to be able to do. Our next tool that's available to us is a functional flow block diagram, or FFBD. And these can really be useful in determining how long or the order that a process should occur in. And particularly, it allows us to show the interrelationship between functions or requirements within a system. Sometimes they can happen sequentially, so one after another, and they have a specific order they need to follow. Sometimes they can operate in parallel, or sometimes there's multiple paths depending on some sort of a decision tree. And so we might have requirement 1, requirement 2 and 3 that can operate here in parallel, and requirement 4 there, for example. So, for example, if we were trying to model the process of a passenger entering a car, we've got action 1 or action 2 there that they can turn the key or push the button on the remote control and use that to enter the car, and both of those will disable the alarm or immobilizer within the car and unlock the door at the same time. We then have a passenger sitting down, we close the door, and we could assign times to each of those and be able to see very clearly what our order is, but also the time required to actually go through this particular process in our functional flow block. Our final tool that we'll briefly look at is our context diagram. And this is something that's used by designers to show that the environment the system is going to be operating in. So we can see all the stakeholders there, all the related systems, external systems, the regulations, external interfaces that this system has to abide by and interoperate with. It's very useful because these external environmental constraints can constrain the system design in all sorts of different ways. So suggested process of how we go about this is essentially to list all the elements, things outside the system that may affect or interface with the system. So whether there's an input or an output from the system, and things or people that may actually affect the system. And we want to group these according to the relationship with the system and how they impact the system or interface to the system. We typically use these ovals to show groupings, and here's an example here. We have, for example, a car alarm system that's sitting right in the middle. And because that's the system and we're really interested in the external environment that this system operates in, we're not showing any of the internals of the system yet. That will come much, much later when we design all those sort of things in. But the car alarm system is fully constrained within the car system. Now, we have the engine marked in there because this car alarm system may have an engine immobilizer to prevent the engine from starting unless the car alarm system is disabled. We'll also need power that will be supplied by our car system to power this car alarm system. Now we have two different people that have a particular interest in this car alarm system, one being the owner or the driver of the car, the other being an intruder. And each of those interact with the car alarm system through the car, so they're actually coming into both the car system and the car alarm system. And hopefully we'll be able to differentiate between the two of them based on how they're actually interacting with this system. Now, if our car alarm system, for example, has GPS to tell a user where the car is at any point in time in case it's been stolen, well, it'll need to interface with the GPS system. Note that the GPS system consists of GPS satellites, so it's a wider system that's not part of the car system directly. And likewise with a mobile network, if one of those common ways that these car alarm systems can communicate with us is via a 4G or a 3G module that can send messages or something like that. Now, we might have other people in the vicinity of this car alarm system, and they won't necessarily be getting into the car system or the car alarm system. They'll be walking past and seeing the lights going off and the siren blaring and things like that. They may see an intruder, they may inform the police that something's a bit sus here. And likewise the police. This car alarm system doesn't directly notify police, but if they're on their patrol and they see a car alarm going off, they may choose to investigate that car alarm system or if it's been reported to them. Our owner driver can report things to their insurance company, and so the insurance is connected through to our owner driver and not directly through to the car alarm system. There may be information in our car alarm system that can be, for example, logs and things that can be supplied to our insurance company as well. So there's a few different tools you can use. There's some more examples of each of them in a textbook, the System Engineering Practice.